Now, in the second part of the proof, so now what I did was I set up the two equations from the previous video. So here's the one where all we did was multiply both sides of the equation by lambda sub k plus 1. Oh, also incidentally, I think I forgot to put the vector symbols on top of the v's, so just keep in mind in the last video, those are vectors, not variables. Okay, but anyway, so we've got the first equation here, right? And again, all we did was multiply both sides of the equation by lambda sub k plus 1. And then the second one, we applied the map to each, to both sides of the equation, so we got this. T of vector 1, and then all the way through T of vector 2, and vector k, and then also the mapping T of vector k, the v of k plus 1. So we got these two equations, and now what we're going to do is we're going to subtract the second one from the first one, and we get this, right? So now again, apply the mapping of each one. So this is going to be what? Lambda 1 v1. This is going to be lambda k, vk, and so on. So I skipped a step there. But what you do is when you subtract and you factor out the vectors, you get this, right? So you get 0 vectors equal to c1 times this difference times v1 plus all the way to c sub k times the difference between lambda k plus 1 and lambda sub k times the vector vk plus c sub k 1, and then this difference. Notice that this is lambda k plus 1 minus lambda k plus 1. So this is going to end up being 0. So this term is going to drop out, right? So what happens is it reduces to a linear combination of the vectors v1 through v1 through v sub k, right? With the leading coefficients c1 through c sub k. Now, when we apply the induction hypothesis, right, we're assuming that for the k vectors, distinct vectors, what? That it's linearly independent. So that means all of these coefficients are 0, right? So that's what I wrote down here. All of the coefficients are equal to 0. But now, we're going to use the fact that all of the eigenvalues are distinct. And so since they're distinct, none of these differences are going to be 0. So how are these products going to be 0? Well, the zero product principle is then going to tell us that the coefficients, c1 through c sub k, must be 0. So what does that mean? If that's true, we go back to the original equation, right? I'll write it up here. So if we go back to the original equation, the 0 vector equals what? c1 v1 plus all the way to c sub k v sub k plus c sub k plus 1 v sub k plus 1, right? We go back to the original equation. Well, now that we know that all of the c's, c1 through c sub k, all those coefficients are 0, all of these go away, right? All of these go away except for the last term. So that's where we're at down here, is we're left with the 0 vector is equal to that last term, c sub k plus 1 times v sub k plus 1, which then tells you that c sub k plus 1 is also equal to 0, and therefore, what? It's linearly independent. The vectors v1 through vk plus 1 are linearly independent, and there is the proof of the result.